to Electricity and Magnetism. This is basically an entire new course. If you're taking this test, and it's an entirely different test, usually this is University Physics 2, the second semester in a physics course, engineering physics course. So it's a little different. This is now a little bit more abstract. We're not dealing with things that are quite as concrete to us. So a few tips. One, read the appropriate chapters. Since we're doing this flipped classroom, it's a little different. Sorry, little interruption. And so, read the textbook. It'll help. It's putting things in a little bit of a different language from what you might hear from me, so pay attention to that. Review these slides. As you're doing the homework, which is now the classwork, go back and take a look at this, reread it. Don't get behind, keep up with the work. It's the idea is build, so don't let yourself get behind. So electromagnetism, it's the science of electricity and magnetism, right? Really simple. Electric charge is an intrinsic characteristic of fundamental particles. This is something like mass, it's something like length. Particles can have electric charge. And we measure it in coulombs, right? It's the basic SI unit for measuring charge. And we have types of charges. There's positive, negative, neutral, right? If it's neutral, that just means that the amount of positive and negative charge is the same. And electric charge is quantized, right? 1.6 times 10 to the negative 19th coulombs. That's the charge on a proton. We deal in quantities, multiples of that. Right? And so then 1 coulomb of charge is the charge on 6.25 times 10 to the 10 to the 18th electrons, right? Micro, nano, pico, those are all the different Greek prefixes, right? -6, 10 to the negative 9, 10 to the negative 12. Don't forget that. And then Coulomb's law, which you learned last year, should be very familiar to you. F equals K QQ over R squared. And now, might be a little new, we're introducing R hat. So it's F equals K Q1 Q2 over R squared, R hat. And again, R hat points away from the particle towards the other particle that is exerting the force. Okay. So, a lot of this stuff is review. The interaction between electric charges. If we have two very small spherical charges, we treat them like point charges. Again, they attract or repel as if everything was concentrated at the center. You're going to see a lot of stuff here that looks like gravity. So keep that fresh in your mind. You see a lot of similarities. If a shell of uniform charge attracts or repels another charge outside the shell, as if all of it was concentrated at the center. And then, this is another shell theorem, right? The charge inside of a shell feels no electrostatic force at all. Just like inside of a spherical shell, there's no gravitational force, right? Zero. Positive charge you create by taking away electrons from an atom, and negative charge you get by adding electrons to an atom. It gives you an overall net positive or negative charge. Conductors are materials where the charge can move freely, and then if a conductor is charged, what happens is all the charge moves to the surface, right? And this is going to be a big difference. You can have a conductor, if it's charged, it's all on the surface, as opposed to an insulator. Insulators, the charge can be distributed throughout the inside of the object. So that's the next one, right? Insulators, the electric charges cannot move freely, and charge is usually distributed within the insulator. So when you're reading a problem, pay attention. Is it a conductor or is it an insulator? Is the charge on the outside or is it distributed throughout the inside of the object? Semiconductors, right? These are materials that have some of the properties of conductors, some of the properties of insulators. Right? And part of it depends on the amount of voltage that's being applied to it. And this is what transistors are made of. And the transistor is the basis of all of our computer technology, digital technology. It can be turned on or off. We're not really going to study this much at all, but it's worth noting here. Superconductors have no resistance at all to a moving charge. And that's only certain materials under certain conditions, usually low temperature kind of stuff. All right, charges move. Conduction is when charges move between two connected objects Induction, there's no contact. Things are not touching, so there's no charge flowing from one to the other. The side opposite the charged object has the charge equal to the charged object. So, for example, if I have, a sphere that has positive charge on it, and I bring that near a larger sphere, all the negatives are going to come here, and all the positives are going to go there to the other side. So the side opposite has the same charge as this one. And this is still neutral overall, but it's been polarized. Okay, and then grounding is when you connect a conductor to the earth and it acts as an infinite charge sink. In other words, all the extra charge just goes off of it. And the symbol for that, which I'm sure you're familiar with, something like that. So this will just, all the charge can go there. Charging by induction in this diagram, right, you have the rod comes close, it polarizes it, and then it's grounded. So all of the negative charge goes to the ground. The positive charges remain because they're attracted to the negative. Then the wire is removed, and now you have a positive charge. So when you charge by induction in grounding, you end up with the opposite charge of the charging instrument. Right? The rod was negative, and then the sphere in the end has a positive charge on it. So again, this next slide is talking about gravitational force versus electric force, and you can see that Fe is kQq over r squared with r hat, and okay. So this is what goes in there, and you see K is equal to the 8.99 times 10 to the 9th newtons meter squared per coulomb squared. But the thing that goes in the other box is this: 1 over 4 pi epsilon naught, and then Q1, Q2 over r squared r hat. So K is actually equal to 1 over 4 pi epsilon naught, and we'll get to this. When we get Gauss's law, we'll see kind of where this comes from. But you need to be familiar with both, because in more and stuff that we do later, epsilon naught is going to become really important. It's called the permittivity of free space, and we'll get there. And so epsilon naught is the thing down below, right? Epsilon naught is 8.85 times 10 to the negative 12th. Coulomb squared per Newton meter squared, right? It's the inverse of the units on K. Okay, and so attraction and repulsion. When two things have the same charge, they repel. When two things have opposite charge, they attract. Okay. And so in example 1, so in this, you can see the force on 1 by 2 is going to be this. And so I just fill in my numbers, right? This is 9 times 10 to the 9th, can round 8.99 to 9 here, times 1 times 10 to the negative 6 coulombs, right? Careful because it says micro there, right? So micro is 10 to the negative 6. Don't forget, we're going to see these prefixes a lot more when we're dealing with these big numbers like small charges or a very large number of objects that are charged. And this one is negative 2 times 10 to the negative 6 coulombs over, we have a distance of 1 meter squared. And so this ends up being negative 1.8 times 10 to the negative 2 newtons. That's the force on 1 by 2. And so this negative here actually means that they're attracting each other. That, if this is 2, the force on this other one is towards this object. Or, opposite the direction from Q2. If this is Q2, r hat is away from this, but negative, so it's towards. And then example 2, it's the same situation, except now this is positive. Oh, and they're 2 meters apart. All right, so here's example 2. This is 2 microcoulombs, and they're now 2 meters apart, which is there. So now we get 4.5 times 10 to the negative third newtons, and that's in the positive direction from charge 2. So that's away from charge 2, and that's the force on 1 by 2. Okay, so for this problem, example 3, you can see we have 2 positive charges and a negative charge. I want to know the net force on Q1 due to 2 and 3. Let's just do a little quick work here and see what we can expect. This is 2 meters, this is 2 meters, this one's farther away, but there are different charges, so the size of the force will depend on that. The force from here to here is that way, right? This is the force on 1 by 2. The force on 1 by 3, right, is going to be this way. So this is the force on 1 by 3. When I add these two vectors, I'm going to get something like this. Okay, I think this is going to be my net force on particle 1. So I'm looking for that. Okay. The force, so I'm going to look for the magnitudes. I'll do the magnitudes and then just do the directions separately after that by using trigonometry. So F1 on 2, right, we're just using K, Q1, Q2 over R squared. And I plug in my numbers, 9 times 10 to the 9th. So this is 25 times 10 to the negative 6 coulombs. And then this is negative 10 times 10 to the negative 6 coulombs. Over R squared, R is 2 meters. We're separated by that. So 2 squared. And I end up with 5.625 times 10 to the negative 1 newtons. The force of 1 on 3, magnitude, right, and put the direction there, is K Q1 Q2 over R squared. Again, 9 times 10 to the 9th. This is 25 times 10 to the negative 6 times 20 times 10 to the negative 6th. And then the distance now is 2 root 2 squared, right? Because this is 2 and this is 2, so Pythagorean theorem gives you 2 root 2. Put that whole thing squared. This ends up being 5.625 times 10 to the negative 1 newtons. So they end up being the same. Now I'm going to do figure out the direction here. Okay, so in terms of the x direction, the force from 2 is all in the x direction. It's in the positive x direction, right? So this is going to be 5.625 times 10 to the negative 1. And then there is no vertical component of the force from 2. From 3, the horizontal component is going to be that times cosine of 45 degrees, right? Or that times root 2 over 2. And so this will be, oh, in the x direction, it's pushing away, right? So this is negative. So negative 5.625 times 10 to the negative 1 times root 2 over 2. And here, this will be also negative because it's pushing downward. So negative 5.625 times 10 to the negative 1 times root 2 over 2. Okay, so I add those up, and this comes out to 0.165, and the net vertical force is negative 0.398 newtons. And so, you know, an easy way of expressing this now is just to use our unit vector notation. So this would be the force of 1, the net force on 1 is 0.165 I minus 0.398 J newtons. Okay. And then if you really feel like you need to get what is the vector not in the unit vector notations, it would end up being 0.431 newtons at negative 67.5 degrees. And both these results, that gives us the vector here that we would expect. Okay, so now example 4, we have two charged particles at the end of a string. Each particle is 30 grams each. We want to find the magnitude of the charge. Notice it says magnitude on each of these spheres or particles. We don't know if they're positive or negative. We just know that they're the same because they're repelling. So they might both be positive, they might both be negative. And let's take a look at this then. If this is the particle, this is the tension, this is the force of gravity, and this is the electric force. So I can put this into like a triangle that looks like this. Okay, so this is 5 degrees, this is 85 degrees. And so then the cosine 80, the tension times cosine of 80 is the electric force. So T cosine 85 is equal to the electric force. The vertical force here is opposite, so that's sine. So T sine of 85 is equal to the gravitational force. Right, now this one's going to be easy to solve. So T is, the gravitational force is going to be 0.03 kilograms times 9.8, or 10. So T is going to be, let's use 10, 0.03 times 10 over sine of 85. And that, well, so that's what T is. And if I take this and I plug this in here, that'll give me the electric force. And so Fe now is 0.03 times 10 over sine of 85 times cosine of 85. And I find this comes out to be about 0.0257 newtons. Right, now that's the force. Now I need to find the charge. The charge is here. So what's this distance from here to here? Well, this is 0.15 meters. Then the distance here is going to be 0.15 times sine of 5. But if I add this plus this, these two together is going to give me 0.3 times sine of 5. That's the distance between them. Right? So Fe is given by K Q over R squared. All right, but realize that it says that they're identical, so they have the same charge. So this is just Q squared. So this is K Q squared over R squared. This now is equal to this. Is equal to Fe. So Q is going to be Fe times R squared over K, and then you take the square root of that. Now we plug in Fe is this, R, we take this and we square it, plug that in, and then K, or 9 times 10 to the 9th. And what we end up with is plus or minus 4.42 times 10 to the negative 8th coulombs. That's example 4. Okay, here's example 5. We have this situation where we've got negative 6 and 15 microcoulombs. Now I want to know where here can I put a negative charge and we don't know what the charge is, just any negative charge, so Q3, so that the net force on it is 0. Well, I know I need to figure out the regions. This, by the way, is going to be a really common kind of problem. So get used to thinking about this. So you think ahead, well, if I have a negative charge here, it's going to be repelled by this, and it's going to be attracted by this. So there's no region in here where, a negative charge will be repelled by this and attracted by this, so it'll go that way. There's no region in here where it's going to be 0. If I go over here, this is closer, and it's a larger charge, magnitude of charge, than this. So here, it'll just be attracted to this, and the force of this won't be enough to repel it. So there's no region over here either where I'm going to be able to put a negative particle and end up with 0 as the force. So I'm restricted to being over here somewhere. So I'm just going to put here Q3, and I don't know what that distance is. But what I do know is that the force from 2 and the force from 1 have to be the same. They have to add up. This one is repelling it, but this one is attracting it. Those two are going to balance out. And so I write this equation, right? The force on 3 by 1 is equal to the force on 3 by 2. The force on 3 by 1 is K Q1 Q3 over, and now what's the distance? This is 2 meters here, and this is our distance x, which we don't know. So the distance from 3 to 1 is 2 plus x. And then the force on 3 by 2 is K Q3 times Q2 over. Now the distance between these is just x. So that's x squared. Now all I'm doing is I'm solving for x. Q3 cancels out. K can cancel out. So this becomes Q1 x squared equals Q2 2 plus x squared. So this is going to get a little nasty. Q1 x squared equals Q2 4 plus 4x plus x squared. So Q1 x squared equals Q2 times 4 plus 4x Q2 plus x squared Q2. Now I set the whole thing equal to 0. 0 equals x squared Q2 minus Q1, because I brought that from the other side, plus, I'll put, this one has x in it, right? So 4Q2 times x plus 4Q2. Now I just plug in the Q2s, and I have to do quadratic formula. And what we end up with is negative 0.77 meters. So I'm at that position. And then the next question, what about for a positive charge? Same thing. Notice it doesn't matter what we put in here for Q3. It cancels out when we start trying to solve for x. So A and B, same answer. You place any charge at negative 0.77 meters, and the net force on that charge will be 0.